Okay, let's go ahead and continue with what we're dealing with in terms of matrices. And we're going to move on to the inverse of 2 by 2, the 2 by 2 matrix. And say, for example, if your matrix is A, then we're going to represent that as A inverse. Okay, so let's go ahead and just take a look again at what we're using A inverse for and get the big picture. Say, for example, if we're trying to solve a system of linear equations, then let's go ahead and take a look at this linear equation here. These two linear equations which make up the system, 3x minus y is equal to 8, and 2x plus 3y is equal to 6. Now, the way that we could algebraically come out with the solution is by either using the substitution or the elimination method. Those are the two methods that we know, algebraic methods that we know. Or we could also go ahead and graph this to find out where the intersection point is, and that would be the graphical method of finding the solution to that system of linear equations. And then the fourth method, of course, would be using matrices. Okay, so how do we go about using matrices? And in particular, how do we use the inverse of a matrix in order to solve the system of linear equations? So what we can do is we can go ahead and change this form of the two equations into a matrix equation, and notice this will be exactly the same thing because that's going to be 3x minus y is equal to 8, and this would be 2x plus 3y is equal to 6. So notice these two here are equivalent. So what we can do then is we can go ahead and call this matrix A, this matrix X, because that's the matrix that we want to try to determine, and let's go ahead and call that matrix B. Now, in order to find the matrix X, notice that I need to go ahead and somehow eliminate the A matrix. So what I can do then is multiply by the inverse of A. The left multiply inverse of A to this side of the equation, and left multiply the A inverse to this side of the equation as well. So notice that when I do that, the A inverse times by the A is just going to be I, because that's the definition of your identity matrix. Times it by x is going to be equal to A inverse times it by B, and since we know that the identity matrix times it by any matrix is just going to be the matrix that is being multiplied to, we know that x can always be solved by just A inverse B. So how do we go ahead and find out what A inverse is? Well, if A is equal to A, B, C, D, a 2 by 2 matrix, then A inverse is going to be 1 over AD minus BC. Okay, so you have that crisscross there. And then what happens then is that these two here are interchanged and negatives are associated with the B and C. And that is going to be your formula to remember what A inverse, how to calculate A inverse. So what we can also do is we can also talk about the determinant of A, and the determinant of A, remember, is just this part. The determinant of A, or we can also go ahead and write it this way, is just that part. So the only part that we're talking about when we're talking about the determinant is just that part. Okay, what's under the 1. So let's go ahead and apply this knowledge then that we have here to this particular system of equations to solve the system. So we know for a fact that A is going to be 3, negative 1, 2, 3. That means that if we go ahead and use this property, this formula here to find A inverse, that's just going to be 9 minus a negative 2, which is 9 plus 2. I interchange these two, and I add a negative, or multiply a negative to both those elements there. So what I come up with is 1 over 11, 3, 1, negative 2, 3. And if I go now use this formula right here, or this statement here, to solve for x, I know that I take 1 over 11 times it by this 3, 1, negative 2, 3, and multiply it to 8, 6, because that's what B was. So if I do that, I come up with 1 over 11, 32. And now remember that this x, which represents that, is actually representative of this. So I go xy is going to be 1 over 11 times it by 32. And so therefore the solution that I have, or the intersection point of these two graphs, is going to be 30, 11, 2, 11. Okay. So that's how we can go ahead and use the inverse of a 2 by 2 matrix to solve a system of linear equations. Now, one last piece of information here. Remember that if your determinant of A is not equal to 0, so in this case here, it is not equal to 0, it's actually equal to 11. The matrix is considered to be non-singular, And whenever you have a non-singular matrix, you have a unique solution to the system. Now, in addition to that, if A, or the determinant of A, the determinant of A is equal to 0, then we say the matrix is singular and there is no unique solution. Okay? So one of the questions that we're going to have to explore a little bit more in class is, what does this mean? If it's no unique solution, what are the possibilities? Especially when you can just go ahead and tell that there's got to be something happening since your determinant is equal to 0 and the matrix A is a singular matrix. Okay, so that's the inverse of a 2 by 2 matrix. We'll see if you can apply this formula here to some of the problems that we have, as well as making sure that we can apply them to solve systems of linear equations. Okay, so we'll see how you do, and we'll take a look at things in class. Alright, see you later. Bye-bye.